Okay, so first off, has anybody seen The Imitation Game a long time ago? Like a 2014 movie? Okay, so I'm just gonna quickly play the trailer for you because it has to do with our topic.
The imitation game. It's a test of sorts for determining whether something is a machine or a human being. Would you like to play? All you have to do is ask me a question.
What did you really do during the war?
Are you paying attention?
This war, we're not winning it. You will lie to your family and everyone you meet about what it is you really do.
What is it that we're really doing?
We're going to break an unbreakable Nazi code and win the war.
Oh.
I'm designing a machine that will allow us to break every German message instantly.
Well, it's impossible.
Sometimes it's the very people who no one imagines anything of who do the things that no one can imagine.
Could machines ever think as human beings do?
Most people say no.
You're not most people.
I'm just a mathematician.
I know a lot of spies, Alan. You've got more secrets than the best of them.
This is serious. They could send you to jail.
What if I don't fancy her in that way?
It's illegal.
I just don't know if I can pretend. We were at war with the clock. Tick, tock, tick, tock.
Damn you and your useless machine.
My machine will work.
Not God, Alan. You don't get to decide who lives and who dies.
So tell me, am I a machine? Am I a person?
Turn that thing off!
Alan!
Am I a war hero?
Burn everything.
Am I a criminal?
So The Imitation Game is based on a true story. It's actually a really compelling movie if you're into that sort of thing. And it's based on a true story of Alan Turing, who lived between 1912 and 1954. He's 41, lived to be 41 years old. And he broke codes during World War II. He used the term Heil Hitler to decode daily crypt, and he created this machine that would basically encrypt things. So he also used statistics to randomize when they would save battles so that the Germans wouldn't catch on to the fact that they were able to send these messages that were crypted. So the way this connects to what we're doing is this idea of crypting is actually a very algebraic operation. And so, for instance, we could do a simple crypt. We're not going to do World War II crypt, but yeah, the Turing machine, exactly. It does seem impossible, but you got to start with a simpler crypt cipher in order to be able to, work towards what he did. And feel free to look into that further. But let's say we just had a simple crypt like this, and every letter was assigned a number like this. And you wanted to, say, write a message to someone, and you wanted nobody else to know what you were writing. So what could you do? Well, you could use these numbers, and you could, say, have a cipher that the other person knows how to figure out. And so then if you use, say, double the number minus 1, and the other person knows that, they'll be able to decrypt it. We're just going to try something here. If you might want to grab a calculator and take just like any 3-letter word or 2-letter or 3-letter word, something simple like and or the or hooray, I don't know. It's a short little word, and take the numbers that correspond to that and cipher it so that it's double the number minus 1 for each of your letters. And then maybe type in your chat what that crypt is. So for instance, if I was going to use the letter R, I would say, well, that's 27. So to crypt it, I'm going to go 2 times 27 minus 1. So I'm going to double 27 and then minus 1. And that's that resulting number is part of my crypt. So 19, 21, 23. So what is the process? If we know that to get to that number, they doubled and minus 1, how do we undo? So this is the do, and this is the undo. So how do we undo doubling and minusing 1? Okay, so how do we undo it? Add 1. We would take our new number, we'd add 1, and we'd divide by 2, right? Because we want to basically oppose the order of operations that we initially did. So we would add and subtract first to remove those because those were done last, and then we would divide next in order to solve. Okay, so if we go 19 plus 1 is 20, divided by 2 is 10, which is our A. And then I think these are in, these actually move up by 2, which I think with the doubling, if we predict that, somebody has said this will be ABC. You can try the others as well. But essentially, so if this is our f of x, this is our regular function, this is the do, then to undo, one way we could see this is if we did y equals 2x minus 1, in order to undo it, we'd want to solve it for the other variable, right? Does that make sense? So essentially, it's kind of like if y is always our like function, then it's almost like we're trying to swap the x and y, and then we're solving it for y again to get our new function that we would use. You can leave them as x and just solve for x as well. I just like to have my y first. So if I add 1 to both sides, I'll have x plus 1 equals 2y. And then I'll divide by 2 on both sides. I'll have x plus 1 over 2. So this is my undo function. And this is actually called the inverse function. So my undo is my inverse. So that's essentially what an inverse function does. It's the code crack for a cipher, essentially. Okay, there's a little more to it, but the basics of it are that. And we would write it then as if f of x was this, then f inverse of x would be x plus 1 over 2. And we would do it by swapping the x and y and solving for y. Some people like to just solve for x and then just rename them afterwards. We usually like to have x as the input. That's really the only reason. But also, this shows you that essentially you are swapping the x and y in the function. And really, that's what an inverse does. The other thing that you can do to check your inverse is something called, what we've learned before, is function composition. So if we compose, if we do f of inverse, or easier to see as like if we plug in f inverse for x in f, it should all cancel out, right? So if we take our 2 times our x plus 1 over 2 minus 1, if we do that, it should give me x back. And let's see, cancels, and then the plus 1 minus 1 equals x. So yes, it works, and I should be able to do it the other way around, plug f into f inverse. Either way, because it's a do and an undo, because of that opposite nature of it, it should all cancel out. So when you do and then undo, it should cancel out. Okay, so that's a basic idea of an inverse function, and you're going to be asked to be able to identify if 2 functions are inverses, to find an inverse function for one of the functions, and then also when we start seeing how they look on a graph, there's something interesting there as well. So the basics is like, okay, if your do is an addition, the undo is, like, what's the undo of that? If you add 2, what's the opposite of adding 2? Minusing 2, right? So the addition Inverse is subtraction. For multiplication, the undo would be divide by 2, right? Like you know these things already. You know the opposites. You know how to solve for a variable. And that's essentially, so for a square, you'd have a root as your inverse. So that's the basics of that. So, okay, what if we had other code cracks? How would you inverse them? Before we do that, actually, I just want to map it out on a graph so you also see what's happening. So I'm still using the same 2x minus 1 example that we had for the code crack. So when you had x is 2, double 2 minus 1 gives you 3, right? So it's kind of like you have x and y, 2, 3. So 2, 3 is a point right here for f, right? Now, what does f inverse do? Well, it basically swaps them, doesn't it? Because, well, we can try it. F inverse was x plus 1 over 2, right? We can see that if we throw 3 in, 3 plus 1 over 2 gives us 2 back again. But we expected that because essentially we were trying to go the other way, right? If our 2 was the number of the letter that we wanted to start with, and we made it into a 3, so that was the do, then the inverse function would be the undo, which would go the other way. So if this was my x and y for my do, then this is now going to be my x and y for my undo. Does that make sense? Essentially, the action is that we swap x and y for inverses. So what does that look like on a graph? If I had 2, 3, and then my inverse was then 3, 2, right? If I keep drawing that line, 2x minus 1, so that starts at -1, goes up 2 over 1, like this whole line was my f. Now if I undo each thing, basically if I swap the x and y for each of them, what's going to happen? So the 2, 3 becomes 3, 2. The 1, 1 stays 1, 1. The 0, -1 becomes -1, 0. Right? So essentially what's going to happen is your x's and y swap, which actually produces a mirror image along y equals x, which makes sense because we're swapping x and y. Okay, so here's another test, is that not only do you take the f and put it in the f inverse, it should give you x back again, but if you graph them, they should be mirror images across the y equals x line. There's a reflection across y equals x. So what that means is if you had, say, something like a parabola that you started with, so in this case, this is our basic function, f of x equals x squared. And if we want to figure out what the inverse of this is. Now this gets a little tricky because not all functions are invertible. Like the line was invertible because there was no problem there, but like let's try and apply this here. If y equals x squared, how do I inverse that? Well, the only thing I can do to both sides to solve for x again, maybe I'll swap it just like I did before, swap, so that I know to solve for y. And then that's how I'm looking for my f inverse. What I can do to both sides there is I could square root both sides, but if I square root both sides, I need to have a plus minus. So what happens then is we get y equals plus or minus root x, which does make sense, but look at what ends up happening when we graph that. A root x, a positive root x, is going to look like this. And negative root x, if you graph all the points, is going to look like that. Okay. So far, like, that aligns with the fact that it's literally flipping across the y equals x line. But there's a problem with that green thing. Is it a function? Is the green thing a function? Does it pass that vertical line test that we were so concerned about in the past, right? No, so no, it's not a function. So we're actually going to have to do something here called restricting the domain. So we're going to have to limit the black part so that when it flips, it's only one half of the parabola and not both halves of the parabola. Because right now, f inverse of x would be plus or minus root x, which technically that's not a function. We can only have one of those. And so we just have to define it. So here's how we do that. I would just write out, okay, we have our f of x is x squared. And then what I'm going to do is I'm going to say, what's my domain and my range for f? And I can restrict my domain so that it only includes a portion. And I can choose that. Literally, I can choose either the right side or the left side. If I choose the right side, then the resulting version will be the top half of the green thing. And then if I choose the left side, it's going to be the bottom half. Okay, but I like to write this little table here for domain and range, because you'll see that they literally will swap as well, just like the x and y does, because domain is x and then range is y. And so if you're swapping x and y, the domain and range will swap as well. Okay, so let's say that we're going to choose only this portion, the positive portion for this. So we actually have to restrict it and say everything from 0 to infinity. So I would say for x greater than or equal to 0. So that's how we restrict the domain. We just state that. Once we state that, now we can proceed as well. So essentially what this means is that in order for a function to be invertible, like so you can take an inverse of it, it must basically, in one way of saying it is, it has to pass not only the function test, that's the vertical line test, but also the horizontal line test. Okay, so it has to pass this test as well, not just the vertical function test. Okay, so let's keep going here. So you go 0 to infinity is the restriction that we just did. And we found that f inverse of x is going to be, in this case, if it's the positive side, it'll be the positive root x portion. And obviously, x will be greater than or equal to 0 as well. So we'll do that in kind of like highlighted green there. So we basically just limited the original so that we could flip it. We could take an inverse of it. We could take just the positive. We could have chosen just the negative. And then we want to fill in our domain or range. So for that purple piece, the domain, the x values are all the x's from 0 to infinity, right? So we got that. And the range was also everything from 0 to infinity. So this is not the best example because it's all going to be 0 to infinity no matter what we do, because now the domain from this will become the range of the green function, and the domain from this will become the range for this part. Like they're literally going to swap. But you can't see that because they're all the same in this example, but we will see that. So making a little table for domain and range is going to help there. Okay, so let's try some more examples. Let's try that first. Okay, so what if you had 3x minus 4? You know, in this case, domain and range are all real numbers, so there's nothing to really do there with that. But can you find f inverse of x for us? And then obviously domain and range are all real numbers because they're lines. If you finish early, you can start trying to tackle this. So my suggestion is just make it y equals 3x minus 4 and then solve for x, or swap right away and solve for y. Either way, you're getting the undo function. Okay, so work on that. And if you're done, then you can work on trying to find f inverse of x here, which is a little more involved because you want to state the domain restriction. A little more challenging if you want to try that. So we can try that. And again, you could swap the x and y right away. Or you could solve for x first. Maybe I'll do it that way, this way. But then you have to remember to swap it later. It really doesn't matter where you swap it, whatever you feel more comfortable with. But I'm going to add the 4 to both sides. Divide by 3 on both sides. And you can see that, okay, this results in my f inverse of x being x plus 4 over 3, which is the code crack for this f. Right, and so that is a kind of 1/3 slope plus 4/3, so that makes sense with this green line there. Okay, so that's basically what inverses are. The second one is a little more tricky, but essentially what happens, what we do know is that this denominator can never be 0. So if that cannot be 0, that limits our domain and means that in our domain, we'll have everything except for when x is 2. And so the other thing that will happen for our range, as you get closer and closer to making a 3, like making it equal to 3 is actually going to end up being impossible. And that's anytime you have equal powers in the numerator and the denominator, it will start to approach, each side will start to approach this asymptote at the very end. So as x gets really big, then you'll notice you'll have like 3 times, let's say 1,000 plus 1 over like 1,000 minus 2. This really doesn't end up mattering because approximately that's 3,000 over 1,000, which is always approximating 3, but not quite 3. And essentially what'll happen is it'll never equal 3. Y's cannot be 3. Like there's no way if you try to put x's in, you'll never end up getting equal 3. So now we'd have y equals 3x plus 1 over x minus 2. And this is the part that we're trying to work on right now, is how do we solve for x? I'm going to multiply both sides by the denominator so that it goes away. And then I'm going to distribute this. Xy minus 2y equals 3x plus 1. And because I hadn't swapped them yet, I'm just trying to solve for x. So a trick here, when you have your variable in 2 different places, typically, even if that y is not a number, I'm trying to get the x's together and the non-x's out. So I get my x's together and my other ones out. So I'll have the 2y plus 1 on this side. And to get my x out, now I'm going to factor it out. And then I'll be able to divide both sides by it. So that strategy will come in handy quite often when you're doing the inverse functions. So now if I divide both sides by y minus 3, I get 2y plus 1 over y minus 3, which is going to be f inverse 2x plus 1 over x minus 3. Okay, so now pay attention to the denominator here. So what is the domain restricted as? X cannot be 3, right? Because it can't be 3 in the denominator because that would make it 0. So another way to actually find the missing range is to trust that an inverse will always swap the domain and range, because this approaches an asymptote of 2 with equal powers. Even if you just based it on the denominators and got the green and the yellow, you'd be able to infer the other one. So let's try some more, because there are a couple other iterations of this. So I think you're probably good with ones like this. You've seen those. That was like our initial code crack. So I think you can do those. Let's try this one. This is a quadratic because it has an x squared. And it has been limited to x less than or equal to 0, which is the left side of the parabola. And if we remember anything about what this parabola looks like from our last class, x squared plus 4, what shifts happened here? Yeah, so it's essentially, there's no x shift, there's just a y shift up 4. So we can kind of anticipate what it looks like. And they've restricted it for x less than or equal to 0, which means they have restricted it to this piece. So just in your head, you can kind of anticipate that the inverse will be all of those points, but the x and y are swapped, which will be a reflection across the y equals x line. So you should get something that represents 4 here and out like that. That's what my prediction is. But we can use the strategies we just used to solve it and to figure out the domain and range. So the domain of f is x less than or equal to 0. You could write it as -infinity to 0 with interval notation if you like. I don't mind either way in this case. And the range is everything greater than or equal to 4. You could write 4 to infinity as a interval as well. And so knowing that, I know that like the range should end up being the domain of the inverse, and the domain of a regular function should end up being the range of the inverse function. Like that's what my prediction is, but then you'd want to double check, right? And you also want to do your kind of backward motion here. So we're going to subtract 4, right? And then now we're going to square root both sides. And now at this point, normally I'd have them plus minus, but because of this restriction here, I have to choose the one that corresponds to that. So that was the minus version. And so I'm going to choose the minus version because of this x is less than or equal to 0 component. So drawing it out will really help you identify which piece we are interested in here. Okay, so that's going to now become our f inverse of x is negative y minus 4. And then our domain and range, we can check it. Essentially, remember, anything under a square root has to be positive. So knowing that, y minus 4 has to be positive. So that means if I add 4 to both sides, y has to be greater than or equal to 4. Sorry, I didn't change that x. See, if you change it first, then you don't forget about it. These are all x. That makes more sense because we've swapped it to an inverse. And so see, that's where you have the domain there. So let's see if that works. Is greater than or equal to 4, right, for this piece. So that works. And it's also less than or equal to 0 for f, right? And that's because it's the negative portion. So yeah, and sometimes you can predict, right? Like if you start with one that's kind of like this, it'll probably end up being a similar type of function. If you think of this one, if you have a root, what kind of function do you think the inverse will be? So what do you think the undo is going to be for a square root? So if I have a root function, most likely, so a root usually looks like half of a parabola. That's just like your basic root x function. And so the squared of that is then going to be the opposite, which is kind of like this, but one side of it, because otherwise it's not a function. So let's try this one. Okay, so see if you can find the f inverse and then figure out what the domain and range are for both. Okay, they've already restricted the domain. You can actually think about this in terms of shifts. I would write it like this, and then you can kind of see inside of the x component, it's taking the regular root x graph and it's shifting it left because remember it's opposite in the x component. Shifted -6 and then like that. So I'm anticipating that the inverse is going to look something like -6 here and like that. So maybe a parabola x squared -6. I'm just anticipating that strictly based on what I know with the graphs and the fact that it will swap x and y. But I can, plug it in and solve for x to find the inverse. So try that out. What do we do to both sides first? So if we square both sides, we're going to undo that root. So we'll have y squared equals x plus 6. And then I'm going to undo the addition of 6 by minusing 6 to both sides. And I get my y squared minus 6. What that tells me is that f inverse of x should be x squared minus 6, which is exactly what I predicted. But now I have to make sure that it matches the restriction that we had. So we had it restricted to the positive side of that curve because it was greater than, and it was also the positive version of the root. And so the best way to now see that restriction is that now we're looking at just the greater than or equal to 0 component. Another way to confirm this restriction is to do your domain and range, and knowing that your domain and range will swap as well. So whichever pieces you know, you'll be able to kind of infer the other pieces. So they told us that f had to have x is greater than or equal to -6. That was the restriction. So right away, that tells you that your range should be y's are greater than or equal to -6 because your x's and y's swap, and they are. And then based on sort of our knowledge of what a root is, the range was y was greater than or equal to 0, right? Because they were always positive. You can't get a negative answer for that. Okay, so usually, let's do a color thing here. Usually you're able to figure out f domain and range, like you've done that before. And the only thing now is that for your f of x, f inverse, they're going to swap. So whatever you know your domain to be, it's going to be your range. Whatever you know your range to be, it's going to be your domain. And then you can check it with the graph as well. So on this green line, which is the inverse, you can see that x's are greater than or equal to 0, and y's are greater than or equal to -6. And on our yellow line, it's the opposite. Okay. Now, a triple check of if these work, you can always check if there are inverses, is remember you can plug one into the other and then see if it works to cancel out to give you x, and then you know for sure it's an inverse. So if I went and threw in f inverse into f, so I took the basic function opening, and then inside this x, now I put x squared minus 6. Let's see what happens. The 6's will cancel out because that gives us 0, and then you have square root of x squared, which is x. So yeah, they cancel out. It should work the other way as well. If you plug in f like that, and you have x squared minus 6, and your x squared is root x plus 6. This will cancel, and then the 6's will cancel, and you'll get x. So this is technically this is a definition for an inverse, is that if you compose the inverse with itself in both directions, you get x, then you know that it is for sure an inverse function because it's going to undo all the operations there. There is actually another type of function that is quite important. It's, again, similar to what you just saw with parabolas, but if you had this given, that's your f of x. What kind of shape is this going to give us? Parabola, yeah. Good, but we don't have it in that format yet. Because right now, for you to solve this for x is going to be incredibly difficult, next to impossible, unless you have the strategy of putting it back into our desired format, which then allows us to peel things away bit by bit, right? And that process, what's the process called for us to get it into this form? Completing the square, right? We need to complete this square because otherwise, like if you try to get x by itself here, because that's what we're trying to do. We're trying to get x by itself so that we can figure out what the undo is for this. But we can't really figure out what the undo is until we have this square put together. Then we can minus the k, divide by a, and then we can square root both sides. Luckily, we have a 1 here, so that's a little nice for us because essentially I'm just going to move this -1 over. And then I have to decide what to add here. So take a moment and think about what I need to add there to complete the square. So remember, half of this squared is going to give you that. So if we add 4, we also have to minus 4. And now this part becomes x plus 2 squared. And then now I have to put this part together, which is -5. Okay, so this actually helps me figure out what the graph might look like because it has no flip or stretch or anything, but it does have a shift and it has 2 transformations, one left 2 and one down 5, right? So you're going to get your regular parabola -2 and -5. And it's going to look, I don't know, something like that, upwards facing. They have given us a restriction in this case. They've told us x is less than -2. So again, we have that negative portion of the root, the left-hand side for all the negative components of it. So that's going to inform which option we choose when we take the square root of the positive or negative. You really can just look at, if that's less than, you're going to take the negative version. If that's greater than, you're taking the positive version. So now we have to get at x. And we can do that now because we can add 5 to both sides and then square root both sides. This would be plus minus, but we are choosing the negative version because of the green restriction, which gives us this x plus 2 equals -root y plus 5. So I'm just going to minus that 2 to both sides. And so if I see through it just because I'm running out of room, it would be my negative root of x plus 5, because I'm going to have to swap that, make it an x now to write it properly. And then there was a -2 as well. But we wanted to get our domain and range. So let's figure out our domain and range for f and for f inverse. So they restricted our domain initially here as x is less than or -2. That should now become my range. Y's are less than or equal to -2. And I should be able to graph that and see it happen as well when I graph this. Because that is the negative version. You could also see this as literally if you plug numbers in, you're always going to have a maximum of 0 minus 2. So it's always going to be less than or equal to -2 as the answer to that function. And then our range was from our original parabola, our range was everything from -5 and up, right? So y's were greater than or equal to -5. And so now we should have x's are greater than or equal to -5. And we can check that. How do we get domain? For our root, inside of a root must be, I'm just checking it so that you see the different ways of checking it. Inside the root has to be positive, so therefore it has to be greater than or equal to -5. So this, I'd say this is one of the sort of more challenging examples that you would get where you do have to complete the square and you would want to inverse it. You can also graph it, and then you could also compose them, like put the f into the f inverse and triple check it, see if it works. But I think here, see, you have a shift of a regular negative root, which is the bottom half of the parabola. It has shifted left 5 and up 2. So it's probably going to be something like that, which should be the direct mirror image. So yeah, we can try these both on Desmos, for instance. I can see that they're a mirror image of each other.